So hi there, welcome back. I'm just going to finish off the little problem with the cubic polynomial that I started in the last video. So on the screen there, you can see where we had gotten to. X is equal to minus 7 plus or minus the square root of minus 151, negative 151, all divided by 2. So we're going to take the next step and we're going to try and deal with this negative 151. So here we go. X is equal to minus 7 plus or minus. And I'm just going to expand the square root part into two parts there. There's the square root of 151 and the square root of minus 1, which we can't process at the moment. We're going to see how we're going to deal with that using the idea of complex numbers. So what we arrive at is that x is equal to minus 7. I'm just going to spit it out over the common denominator, plus or minus some idea called the square root of minus 1. We don't know what it is, but we're going to give it a label, and the label that we give it is I. And then the square root of 151, all divided by 2 there. So when we take the square root of 151, we get, on my trusty here HP11C calculator, we get 12.2882. So let's just rewrite this out here. X equals minus 7 over 2 plus or minus I, whatever that is, times 12.282 all over 2. Come across to this side here then, we get that x is equal to minus 3.5 plus or minus, let me just make sure I've got that there, plus or minus 6.1441. That's all divided by 2. So our two roots then, if we write them out, are going to be minus 3.5 minus 6.1441. Let me just go back and remember that that has got an I on the end. 6.1441I. And that's number 1. And the second root is minus 3.5 plus 6.1441I. So those two numbers are the roots. Now we can't do anything much with those two numbers because we've got different parts to them. We have a real number here, minus 3.5, and we have this number here, which is related to what I is. So let's take a look at some possible properties of I so we can learn to see how we can deal with that and what does it actually mean. So let me just move my screen up a little piece. Let me just do that. Now, what is I? Well, let's take a look. If I start off with the number 1 and I multiply it by I, then I'm going to get to a number called I. If I multiply it by I again, then I'm going to get to minus 1. That's by definition. I is the square root of minus 1. If you square it, you're going to get minus 1. And then if I multiply again by I, then I'm going to get minus I. And if I multiply by I again, okay, what I'm going to get is 1. And then we can just repeat. We can repeat the multiplication by I as many times as we want. But the important feature to note is that we've gone in a cycle. We've gone from 1 to I to minus 1 to minus I and back to 1 again. And we can visualize this idea by giving I an axis of its own in some sort of diagram. So I'm just going to draw here an axis onto which I'm just going to put some real numbers. That's meant to be one of those symbols for an R. I'm going to put a 0 in the middle. At this side I'm going to put a 1, and over here I'm going to put a negative 1. And as we're going in a circle, we might as well use this whole idea of going in a circle to put an I up here and a minus I down there. So we don't know what I is. We can't work with it very much. We do know that it has these interesting properties. So if I want to put any particular number which has got I in it, then I can plot it in two parts. I can plot the real part, which hasn't got any I in it, and I can plot what we're going to call the imaginary part on the I axis. So this plane here is what we call the complex plane. And it's called the complex plane because we've actually got numbers now that are made up of more than one part. And that's all the word complex means, made up of more than one part. That may mean that it's difficult to deal with, but in this case, all I mean by complex is a number made up of two parts, a real part plus an imaginary part. So all numbers can actually be represented by this idea. So let's now plot our roots that we've got. We've now got three roots for our cubic polynomial. We've got 7. You remember that's the very first one. The first one was 7. We've got the second one, which is minus 3.5 plus 6.1441 times I. And number 3 is minus 3.5 minus 6.1441I. And we can plot these on our complex plane. Clearly it's going to be a bigger scale than the one that I've drawn there. So let's just do that. Let's make ourselves another complex plane here. Real numbers going along the page. A 0 in the middle. And we're just going to choose this point here, which is going to be minus 3.5. And across here could be plus 3.5. But we're going to go out a little bit further because we're going to reach the 7 out there. And then because this is our I line here, we're going to say that that number there is 6.1441I, and this number here is minus 6.1441I. So our first root there is minus 3.5 plus. Let me just turn off that badly designed Microsoft whiteboard feature. The first one here, minus 3.5 and plus that. So our first root is, our first complex root, x2, is up here. The second one is down here. So that's x3. And our very first root, the x1, is somewhere over here. And those are the three roots of our original cubic polynomial, which I'll just remind you is a cubed plus a is equal to 350. Last step then, if those are the three roots, we should be able to put them back into this equation to get 350. Now that's fair enough for the 7 here. We can show that very quickly. I'm going to show you that it's also true for this root up here. Yes, this one here, minus 3.5 plus 6.144i. So to do that, I'm just going to bring up another little web page with a calculator that handles complex numbers. So here I've come out to a product on the web called Symbolab, which allows me to do stuff with complex numbers. Unfortunately, with my nearly 30-year-old HP, I can't do complex numbers. So I've written in here the actual roots, minus 3.5 plus the square root of 151 over 2 times I cubed plus the same thing now, but just the a on its own. And when you press go, what you get is hopefully the correct answer, and we bring it up. And there you go. The correct answer is 350 plus 1.4 e to the minus 14. So that is effectively 0, 1.4 times 10 to the minus 14i. So we've managed to get the answer correct. We've got the 350 out using one of those complex roots. So the complex roots work. Whether we understand or appreciate the nature of I is not important, but that's just one of those things we can do. Okay, so on to the final step of this little video. See you in a minute. So for this last step, I've opened up a product called Desmos, freely available graphic calculator out on the web. And on this screen here, you can see a set of axes, and on it I've drawn actually the square represented by our little formula. Okay, so there's the little bit in the top corner, x squared, then there's 3.5x, 3.5x, and then this piece on the corner. So what have I got here? I've got a set of coefficients, a equals 1, b equals 7, c equals 50. So that's x squared plus 7x plus the 50 at the side. And when you change these values, we can change the shape of the little box. So here, if I actually come back out here and I change that down to, say, 40, okay, the size of that box actually changes. Okay, so here I can move this up and down, and then I change the value of c, the constant at the end. That square in the corner changes its size. When it gets to a certain size, it actually becomes the correct size for the square. And in this case, that correct size is going to be 12.25. Okay, we know it's 12.25 because when we take a square, okay, up here, then the 7 gets split evenly between these two boxes, the top right box and the bottom left box, which means that that square has an area of b over 2 squared, which in this case is 7 divided by 2 is 3.5, and then 3.5 squared is 12.25. So I've actually drawn what these things actually look like. So I'm just going to move this back up to 50, the c value back up to 50. You can see the square changes, and I'm going to turn on that chart there. There you go. That is that quadratic function plotted. Okay, and the vertex of that quadratic function is going to be minus 3.5, right? The negative of half of the b value. So here I'm just going to plot that line. There you can see that line goes right up and down minus 3.5, and this one here is the actual square that is correct for x squared plus 7x. I'll turn that one as well, and you can see here this one is the perfect square, we call it. And we're going to see something happen now with the red square as I bring down c, bring down c, bring down c, bring down c. I've gone a bit too far there, back it up, right? And if I make that 12.25, then what you can see is that the red line appears to have disappeared because it's now the same as the blue line. We can turn the blue line off briefly, and there's the red line hiding exactly behind it. But when you get the blue and the red together, then this square in the bottom is the right size. You have completed the square. That's what the action completing the square means. So what I'm going to do now is just bring this back up to there and explain what this point here is. This point here, 37.75, is exactly 1/4 of 151, which you might remember is the number under the square root sign. So when we actually move this up and down, okay, the numbers that we're getting are actually the difference between the perfect square and the square with a different number in it. You can move that up and down, even go down below there. So that is just an illustration of what's happening. What I'm going to do is actually also show you some labels that I've created, which can illustrate this happening in Desmos. Turn that one on and turn that one on. And then as I go back up here and move this backwards and forwards, you can see that the labels track down with the correct formula up and down like that. And the last part then is these labels here. Turn those labels all on. And what they're doing is, if I get myself back into the right place, explaining what's actually happening here as we move C up and down. So as I move C up and down, right, the current area of the little square here is 38.4. Okay, the square root here is represented by these numbers here. The difference is 26.15. So I'm expecting 12.25. I've got 38.4. The difference is 26.15, and the square root of that difference is 5.144. And that number there is the actual root that we're looking for. Let's just show you that. If I bring that back up to 50, notice that that is 6.144, which is the number that we got in the complex plane, except we're not in the complex plane for this particular problem. So by taking a look at that and playing around with those numbers, you can see a little bit about how there's a relationship between these equations, between the square and the big area in the bottom corner, and what the actual lines look like. So I hope you found that useful. What I will do next is actually explain a little bit how I made these labels that track the curves up here. But for now, that's enough. Take care.